In this video, we're going to get even more appreciation for why the periodic table of elements is so useful. And in particular, we're going to focus on groups of the periodic table of elements. And when we talk about a group, we're just talking about a column. And as we'll see, even though the elements in a given column might have very different atomic numbers, they all have similar properties. And the reason why they all have similar properties is, in most cases, they have the same number of valence electrons. Remember, valence electrons are the reactive electrons, the ones that might interact with other things. And because elements with similar valence electrons will have similar reactivities, they will form similar ions. And they will have similar roles in ionic compounds. Now, for the sake of this video, I'm going to focus most on the extremes of the periodic table, the groups at the left and the right, because those are the closest to having a full outer shell, either by losing electrons or by gaining electrons. So just to remind ourselves, what does it mean to have a full outer shell? Well, in general, people will refer to the octet rule. For our second, third, fourth, fifth, and on shells, you're full when you have 8 electrons. The major exception to the octet rule is the first shell, whereas it is full with 2 electrons. So helium, even though it only has 2 electrons, is very, very, very stable. And the major data point that we have around this octet rule are the group 18 elements right over here, also known as the noble gases. They're known as the noble gases because they're very unreactive. They're very content. They don't want to mess around with anyone else. And that's because all of the noble gases have full outer shells. Helium's outer shell is the first shell, and it's full. Neon's outer shell is the second shell, it's full. Argon's outer shell is the third shell, and it's full, and so on and so forth. Now, if we go one group to the left of the noble gases, we get to the halogens. Now, the halogens have 7 valence electrons. So you can imagine they're only 1 electron away from having an electron configuration like the noble gas to the right of each of them. So these halogens right over here, these really like to attract electrons to form a negative ion or an anion. So you'll oftentimes see fluorine as a fluoride anion. So it has a -1 charge. Or you'll also see chlorine with a -1 charge as the chloride anion. And I could go on and on. You'll often see iodine gain an electron and have a -1 charge. If you go one step to the left, the oxygen group, oxygen, sulfur, and on, these elements have 6 valence electrons. So it's still easier for them to have a full outer shell by gaining 2 electrons than by losing 6 electrons. So these elements also like to attract electrons. So you can see oxygen as an oxide anion, has gained 2 electrons. It swiped it from somebody else. Sulfur as a sulfide anion. Now, if you go to the other extreme of the periodic table, if you look at group 1 elements, they have 1 valence electron. And especially the ones that you see in red here, which are known as the alkali metals, it's much easier for them to lose an electron to have a full outer shell than for them to gain 7 electrons. The reason why hydrogen's a bit of an exception is it doesn't have to gain 7 electrons to have a full outer shell. It has to gain 1. So hydrogen could lose 1 and essentially have no electrons, or it could gain 1 electron and it would have a full outer shell like helium. But when we think about ionic compounds, these alkali metals are really some of the most interesting participants. Because as you can imagine, for them to get stable, they want to give away an electron. So you're very likely to see them having given away an electron and having a +1 charge. So you'll oftentimes see a lithium ion with a +1 charge, a sodium ion with a +1 charge, a potassium ion with a +1 charge. And that's in general true of all of these group 1 elements. Now, what about these group 2 elements, also known as the alkaline earth metals? Well, once again, it's easier for them to lose 2 electrons than for them to gain 6 to have a full outer shell. So you'll typically see beryllium having a +2 charge. It would have lost those 2 electrons. Magnesium as having a +2 charge. Calcium as having a +2 charge. Now, given that, how would you expect things on the left and things on the right to form ionic compounds. So you might guess, if you have an alkali metal in the presence of a halogen, things could get very reactive. And in fact, things will get very reactive because these want to give away electron, these want to take electron. And that's what will happen. The electrons will leave the group 1 elements, and then they will go to the halogen. And in the process, it might release a lot of energy, but what you'd be left with is an ionic compound. For example, lithium loses an electron and has a positive 1 charge. That positive ion would be very attracted to a chlorine anion that has just gained an electron. Maybe it's the same electron, or it swiped that electron from another lithium atom. And so these two things would be attracted, and they could form lithium chloride. And all of these alkali metals could play that same role in this ionic compound as lithium. So it's also typical to see sodium chloride, that is table salt. It's also typical to see potassium chloride, so on and so forth. And on the other hand, fluorine or bromine or iodine can play a similar role as chlorine. So you could see something like sodium iodide or potassium iodide. Once again, the alkali metal would have lost an electron, the halogen would have gained an electron, and then they're attracted to each other and forming these ionic compounds. What kind of ionic compounds might be formed with these group 2 elements? Let's take calcium, for example. It's not unreasonable for calcium to lose 2 electrons to have a stable outer shell, to have an electron configuration like argon. So if it loses 2 electrons, it has a positive 2 charge. And you can imagine those 2 electrons get lost to 2 different iodine atoms. So each of them have a negative 1 charge, so times 2. And then what type of ionic compound could they form? Well, you could have 1 calcium and then 2 iodines. So calcium iodide is actually an ionic compound you would see. It has a neutral charge overall because calcium has a positive 2 charge, and each of the iodines have a negative 1 charge, but then you have 2 of them. So it is neutral overall. What might calcium do with oxygen? Well, calcium likes to lose 2 electrons. Oxygen likes to gain 2 electrons. So you could see something like calcium oxide. So I will leave you there. The big picture here is the column in which an element is tells you a lot about its reactivity because it tells you in general how many valence electrons it has. And atoms are most stable when they have a full outer shell, and so that helps you predict, hey, is it easier for them to lose electrons and form a positive ion or gain electrons and form a negative ion? And then from that, you can make predictions as to the types of ionic compounds that could be formed with the different elements.